In this video, I will talk about TrackFormer as a multi-object tracking with transformers, which is published in CVPR 2022 from Technical University of Munich and Facebook AI Research. So yeah, let's talk about that. Before talking about how TrackFormer works, let's just first talk about the previous attempts that researchers have tried for the task of multi-object tracking. So I'm talking about the general ideas behind it before talking about how TrackFormer deals with that. The first approach is called tracking by detection. In tracking by detection, let's just assume that we have two frames, frame t and frame t plus 1, and our goal is to track these objects, which is in this case these people. So the way that we do this is that at first we apply some object detection algorithm for each frame separately, and that algorithm should give us some bounding boxes. And then for the first frame, which is the frame t, we assign some track IDs, which I will show you here with different colors. And for finding the association between frame t and frame t plus 1, we consider each bounding box as a separate node. And by applying some graph optimization algorithm, we just try to find some association between these nodes and track the identities. But that's just some general idea behind it, and I guess that's enough for understanding the main idea. And the second approach is tracking by regression. And in tracking by regression, we have some bounding boxes with a unique identity at frame t, and for finding these identities at next frame, we just first project the same bounding boxes at the same location to the next frame, and then we use a regression head just to move these bounding boxes and find those identities. So yeah, these are the main two approaches that were used before, and now we have tracking by attention, which is this TrackFormer paper. But before talking about the TrackFormer details, let's just talk about the DETR paper, which is another paper from CVPR 2020, which is for end-to-end object detection with transformers. The reason why I like to talk about this architecture is that TrackFormer basically tries to extend the idea of these DETR for videos and tracking the objects. So we just need to know how can we detect the objects, and then following by that, how can we track those identities. Looking at the detail, at first we have a backbone, which is a convolutional neural network that predicts a set of image features. And these image features should have a higher semantic compared to the original image and can better represent what's happening in the image. And like the vanilla vision transformer or VIT, which I also have a video for that, we divide these image features into equal size patches, and we consider those patches as a separate token that we can give to a transformer encoder. But since transformer encoder uses multi-self-attention and they do not care about the order of the input, but we care about the order of the input, we add this positional encoding, which I also have another video for that. But anyway, we have this transformer encoder that receives these tokens, which are a patch of the image features, and after a couple transformer encoder layer, they generate a set of tokens again. But these tokens should now have a better understanding of what's happening globally in the image. So the backbone should give us a representation that locally captures what's happening in the image, and following by that, the transformer encoder should globally understand what's happening in the image. But anyway, until now, it is very similar to what we knew from vision transformers, but now we have a transformer decoder. And this transformer decoder is kinda something new in this paper that receives two sets of inputs. One of them is object queries, and the other one is the encoder output. And these object queries should represent the potential objects that might exist in the image. So if I give it 100 object queries, that basically means I have the potential to detect a maximum of 100 objects in the image and nothing more. But how? Let's just see what's happening inside this transformer decoder. So inside of this transformer decoder, we have a multi-self-attention, which, like always, it receives a query, a key, and a value, which all of them are these object queries. So what about the transformer encoder output? We have another multi-self-attention following by that, which the query actually comes from the output of the previous multi-self-attention. And the key and value is coming from the encoder output. So if you have a good intuition of how multi-self-attention works, you should know that the query basically should say where should we attend to in the image, and the key and value is our image, which is the encoder output that has a good representation of the actual image. So basically, these object queries are initially just some random vectors which should also be learnable. And throughout training, they should learn an optimized representation of objects with different aspect ratios, for example. And by using this transformer decoder, after a couple times, they output a set of tokens which should now represent an actual object that might exist in the image. And to understand whether there is an object or not, we are using a feed-forward network just to give us a confidence score to see whether that token represents an object or not. So in this example, we have 4 feed-forward network, and the first and third one are having a confidence score above some threshold. So they say that we are representing an object in the image. But for the second and the fourth feed-forward network, they output a confidence score below the threshold. So they're saying that, yeah, we are representing somewhere that probably there is no object inside that. So yeah, since the first and third one are representing something, they are using different feed-forward networks just to give us some X and Y and width and height just to represent those bounding boxes. And yeah, that's the whole idea behind this DETR. Hopefully makes sense. I mean, someone could come and say, why are we using these object queries? What happens if I just only use the output of the transformer encoder as the input of transformer decoder? I mean, that could work, but these outputs of transformer encoders, they are only representing a single patch of the image. And what if for a single patch we have multiple objects within it? So by using that technique, we cannot represent all those objects, only one of it. But with this technique of object queries, we are flexible. We can just extend the number of object queries and represent more objects in an image. Hopefully makes sense, because from now on, we just want to extend this idea for multi-object tracking. So now's the time to talk about this TrackFormer idea. In TrackFormer, given the first frame at time 0, we again pass it through a CNN architecture to capture some local information, followed by a transformer encoder to extract some global information. And we again have a transformer decoder that receives the transformer encoder output and some object queries. And it just predicts some output tokens which are responsible to represent the potential objects that might exist in that frame. And in this case, we have 4 object queries, and the first, third, and the last one are representing different people that they are just walking in this image. But for the second token, since it has a confidence score below some threshold, we consider it as a background. So until now, it is exactly like what we saw in DETR. So the difference emerges when we have the next time frame, let's just say frame t-1. In frame t-1, we again pass it through a CNN and transformer encoder, but for the transformer decoder, not only we have these object queries, but also we pass the output tokens of the transformer decoder in the previous time frame. So this is the idea. Since this red token is representing this person at the previous time frame, it should represent the same person again at the next time frame. So when we look at the transformer decoder output, it is referring to the same person again. And likewise, the green token and blue token are referring to the same person that they were referring in the previous time frame. And by doing that, we are tracking it, because we are just having a unique token that we can just assign a unique ID and track that over the course of the video. But what about these new object queries, these 4 ones that we are seeing here? Well, these are responsible for finding the new persons. For example, as can be seen, there is one person that it is coming from the left side of the video. So one of these object queries are responsible to have a confidence score above some threshold and refer to that person. I mean, it is not a constraint to have only one token, right? Because we might have like 2 or 3 tokens that they are having a confidence score above some threshold. But by applying the technique such as non-max suppression that we were applying before in object detection, we are just picking the one that has the highest intersection over union with the ground truth. But that's are the concepts of the object detection that I covered in the other videos. So yeah, that's about tracking these people. But what if one of these people leave the scene? Well, in that case, let's just say we have a time frame at t. We again pass it through a CNN and transformer encoder, but for the transformer decoder, it receives 4 tracking tokens, but the blue one, since it is referring to someone who just left the scene, when we look at the confidence score, it should be below our threshold. It should not refer to anything in that time frame, and we can simply ignore that and consider it as a background class. Seems easy, right? But here comes the challenge. What if this blue person who just left the scene come back after a couple time frames? Well, we have these 4 object queries, so those are responsible to find that person, right? But the issue is that when we're referring to that person, we are not considering it the same person that they used to be in the previous time frames, because we are assigning them a new tracking ID. And that's the issue, right? Because that's the same person, but we are considering it a new person. So the authors, to kind of mitigate that issue, they just said, even though this third token has a confidence score below the threshold, we can kind of pass it to the next time frames. I mean, to the next couple time frames. And if that person comes back, then that particular token should again refer to that person again. And by doing that, we can track the identity. And that's the solution, right? But again, that's having some limitations. What if that person leaves the scene and comes back after a minute or 2? Because by that time, we are surely removing that token and we consider that as a new person. But yeah, that's a challenge that this TrackFormer architecture cannot resolve that. So yeah, that's the general idea behind this TrackFormer model. The next thing is TrackFormer training, the way that we should define a loss function and optimize the weights of this neural network architecture. And I warn you, this is a bit more complicated than what I just presented, but don't worry, because all of it makes sense. And just sit tight, we can understand it together. So the first thing that we should do is bipartite matching, which we should do it before computing the loss function. But what is this bipartite matching? The goal is to find a mapping that maps a ground truth I to a prediction J, and let's call this a map pi. So why do we have this mapping? Because we might have an object that is the first object in the ground truth, but that particular object might be the third object in our prediction. So we should have a mapping that maps the first object in ground truth, which is I equals 1, to a prediction J equals 3. But why do we need to do that? I mean, in object detection, we do not care about the orders, and as long as we have a bounding box that covers a particular object that we have it in our ground truth, we are okay with that. But in tracking, since each object has a unique ID, we should have this mapping that maps a ground truth to a prediction. And in all the time frames, we should use this mapping so that we do not mix those identities. Hopefully makes sense. And the way that we should gather this and the way that we can define this mapping is that we have two approaches actually. One of them is track identity, the other one is minimum cost mapping, which both of them are happening during training. Track identity is simple to define. I just did it to you, that I said we are passing some output tokens from the output of the transformer decoder to the input tokens of the next transformer decoder. And I said the red token should represent the same object as it used to be in the previous frame. And that's how we track the identities. So that's simple to define, right? So for the objects that we saw them before, we just can simply track them this way. But the other thing is minimum cost mapping, which for the objects that we just saw them right now in the current frame that we didn't see them before. So since these are new objects, we should have some minimum cost mapping to map a ground truth I to a prediction J. So to sum up what I just said, we have three different scenarios. The first scenario are the KT, which are the objects at the time frame t, intersection with the objects at time frame t-1, which are the objects that we are seeing in both time frames t-1 and t. And we are using this track identity just by passing those output tokens to the next input tokens to track those identities. The next scenario is for the objects that we are seeing them at time frame t-1, but those are not visible anymore at current time frame. And we just simply match them with background class because our network should predict a confidence score below the threshold and we consider it as a background. And the final scenario is for the objects that we are seeing at time frame t right now, but we didn't see them before at time frame t-1. So in this case, we are using minimum cost mapping for these objects that they are just became visible. And let's just say these objects that they are new are K object, a set of objects that they are new. For these new objects, we should find a mapping. And the way that we define this mapping is this formula, that we should find a mapping sigma hat, which is an optimal mapping that comes from this term, argmin of sigma, which says we should find a mapping that gives us a minimum of some term. What term? This term. So this term says for each object ki that we have in our set k object, which are these new objects, we should apply this cost match. And when we sum all these costs together, different mappings should give us different values. So we are finding a mapping sigma that gives us the minimum cost. And that makes sense, right? So what is this cost match? This cost match receives two inputs. The first input yi is the ground truth, and the second input y hat is our prediction. But note that for the prediction, we are using sigma I as our index. So this sigma I should receive a ground truth index I and give us a prediction j. And that prediction and the ground truth should have the minimum cost, which is the point of mapping, right? Finding some prediction that it is most similar to the ground truth. And that's what our network is representing. But how can we define this cost matching? They say this cost matching is sum of two terms. The first term is for cost of classification, and the second term is for cost of bounding box regression. For cost of classification, this CI receives the index I from ground truth and says which label that ground truth is referring to. And this P hat is the probability distribution that one of the tokens is predicting. Which token? the token that comes from the output of this sigma I. So sigma I receives the index I of ground truth and predicts an index j. And that index j should be one of these 4 tokens in our output. For example, let's just say it is the third token. Then we pick that third token and see what is the probability distribution that it has for different classes. For example, the person, cat, dog, or even background. And since CI is representing a person, we are expecting this probability score for person to be the highest. So since we are expecting the highest, but at the end we are caring about the cost, we are having this negative sign before that. So we want to maximize the probability score or minimize the negative of the probability score. And the next term is for bounding box regression, which receives BI as the bounding box coordinates of the ground truth and B hat, which is the bounding box coordinates for the prediction. Which prediction? The prediction that comes from this sigma I. And for finding the bounding box cost, they are applying these 2 terms. The first term is L1 norm, and the second term is the intersection over union between the ground truth and the prediction. And don't think about this sigma hat as a neural network thing or something. It's just a simple pair that the first element is the ground truth index and the second element is the network prediction. And as long as that satisfies this constraint, which has the minimum cost of classification and bounding box regression, we are okay with that. So this is bipartite matching. After having that, the next thing is applying the loss function, which is set prediction loss. And this set prediction loss is having this formula, which they call it MOT loss or multi-object tracking loss, that receives Y as the ground truth, Y hat as the prediction, and this pi as this mapping from the index I of ground truth to the index J of the prediction. And they're applying this sigma that the n is actually the number of objects that they are new plus the number of tracking objects. And they're applying this L query, which is this. And in this L query formula, note that the index I is now the prediction, not the ground truth index, because it is completely different to bipartite matching. And for the prediction I, it says if that prediction I exists in this pi mapping, then that simply means that there is a mapping from the ground truth to this prediction, and then we apply this term, which is a classification loss plus bounding box loss, which is exactly similar to minimum cost mapping. But for the cases that if I does not exist in this mapping pi, then that means that bipartite matching didn't find anything for that. And that basically means that that's the background. And we just apply this term, which says the 0 class, which is the background, should has the highest probability for that token. And yeah, that's the whole thing you should know about the loss function. The next thing is track augmentation, because we can apply some data augmentation technique just to boost the performance. And the goal is to enrich the set of potential track queries during training. So let's just see what they are doing. The first thing is that the frame t-1 is sampled from a range of frames around time frame t. So when we have 2 consecutive frames, for example the frame t, instead of using the actual previous frame as our previous frame, we are picking one random frame in a round of it. But why do we do that? Because we can now simulate the camera motion and low frame rates. So let's just say the frame 100 is the current frame. Instead of picking the frame 99 as the previous frame, let's just say I pick the frame 56. So since the frame 56 and the frame 100 is around 1.5 seconds away, that the objects that they are existing in that image, they are in a completely different position. And that kind of simulates the low frame rates. And also when I move the camera, the position of objects changes, and it kind of simulates that as well. The next thing is sampling false negatives. And in false negatives, it says, For example, let's just knowing the fact that this blue token is pointing to this object, we do not pass it to the next frame. So we just pass the red and green and not blue. But what's the point of it? Because if we don't pass that, then the transformer decoder does not receive the third person as the input. So now it is the responsibility of these 4 object queries to predict the position of that person. And by doing this, we kind of encourage the model to have a better ability to detect new people that they are appearing in the image. And the final thing is adding false positives. And in false positives, it says, for example, even though we know that the second token is not representing any object, let's just pass it to the next frame. And if we pass that to the next frame, the transformer decoder should now think that there is an object. But we are expecting that for the corresponding output, the confidence score to be below some threshold. And therefore, by adding these false positives, we kind of encourage the transformer decoder to kind of have a strong ability to be robust against these false positive mistakes. And if we pass that, it should be strong enough just to remove that object from the scene, because it doesn't actually represent anything, right? So that transformer decoder should not assign a high confidence score for these false positives. And yeah, that's the overall thing. Now we can talk about the result. The first thing is the result in MOT17 dataset, that there are lots of metrics to assess the differences between this TrackFormer and the other state-of-the-art, but the popular one is MOTA, which I also provided the formula, which is 1 minus this term, that the denominator is the number of ground truth at time frame t, and the numerator is all of the bad things that can happen, which is false negative and false positive and ID switch. And in ID switch, it is easy to define. Let's just say we have one object that it is moving from left to right and another object that it is moving from right to left. When these two objects are very near to each other, it happens for the neural network to mix the identities and assign a different tracking ID. And in that case, we are saying that ID switching happens. So yeah, that's all the bad things that can happen. And we sum all that up, divide by the number of ground truth, and 1 minus that is the MOTA. The other thing is MOTS20, which is the same task, but instead of object tracking with bounding boxes, we track them with segmentation masks. And yeah, it appears that TrackFormer is also very good. And they also did a qualitative experiment comparing TrackFormer with TrackRCNN, which, as we can see, they are very similar, except that the masks that the TrackFormer predicts are have a better quality compared to TrackRCNN. But yeah, that's it. And yeah, that's the whole thing I needed you know about this TrackFormer paper. If you enjoyed it, don't forget to like and subscribe. And until the next video, goodbye.